our lesson only audience. Priya, could you please fix this?
I think that she should just tap the headset sign, then it will be okay.
Thank you, Dr. Roshan. I think something is happening.
Hello.
Yes. Hello? Hello, Dr. Ghasemi.
Hello.
Hello. We can hear you very well. You can start now.
Hello, everybody. My name is Masoumeh Nodehi from IPM. First of all, I would like to thank organizer for inviting me for this nice meeting. I'm going to talk about testing Kerr black hole hypothesis with X-ray reflection spectroscopy. This is outline of my talk. First, I'll introduce iron line method, then motivation, our simulation, neutron star iron line, KTN iron line, conclusion, in the end, a conclusion and summary. What is iron line method? Geometrically thin and optically thick accretion disk emit fluorescence narrow line by height X-ray photon of corona. The strongest line in iron Kerr alpha line, which is at 6.4 keV for neutral atoms. This emission line is prominent feature in X-ray reflection spectra. This emission in the inner region of the accretion disk would be broadened and asymmetric due to a spatial and general relativistic effect of compact object there. As you see in the left panel, here for the Newtonian case, when the emitting matters move with non-relativistic velocity, and it is Newtonian case, there is the same flux here. For this part is blue part, this part is approaching us, this part is red part, this part is going away from us. If we add a special relativistic effect, the blue part has a peak flux and the red part has a less flux. If we add general relativistic effect, all the line would be shifted to the redder part, would be shifted to the and make it redder. All these profiles together give us a line profile that is asymmetric and broadened. This is the first clear detection of iron line by Oscar in 1994, and as you see, it is asymmetric and it is broadened. This case is consistent. This fit is the source is MCG 63015, and this fit is consistent with maximally rotating Kerr black hole. Why do we need this method? Iron line symmetric profile, iron line symmetric broad line profile provide us a powerful technique to probe geometry of space-time near both stellar mass black holes and supermassive black holes, and provide us the opportunity to test a strong gravity regime. Currently, we have data to measure spin and inclination of black hole candidate using this method. On the other side, astrophysical black holes are thought to be Kerr solution of GR, but the Kerr geometry have not yet verified. In general, observational tests of non-Kerr black hole candidates are parametrically degenerate, thus any deviation from Kerr spacetime have to be vanished to verify Kerr hypothesis. And current available data of iron line are parametrically degenerate to test non-Kerr black holes. Near future enhanced observational facility will provide us better resolution and possible constraint of deviation from Kerr geometry and test of a strong gravity regime. This is our simulation. We use a ray tracing code in our simulation. We have two Cartesian coordinates in it. One Cartesian coordinate, this is this prime coordinate that is in observer plane. we detect the iron line here. Another coordinate is on the compact object without prime coordinate. The distance is d and the viewing angle is I. We fire photon from every point of image plane, and photon 3 momentum is perpendicular to the image plane. Photon trajectory are numerically integrated backward, starting on the image plane to the black hole with initial momentum k naught. Here we use this method with adaptive state sizes for to solve our equations. This is our initial condition for the ray tracing code. And for the iron line part, we measure photon flux number density as this equation. E is a specific energy of specific energy of observer. I is a specific intensity. D omega is element of solid angle. E is for emitter, and O is for observer. All the information about the relativistic effect are encoded in G factor, which is defined in this way. It's a function of metric component GTT, GT phi, G phi, and omega, and it is a function of lambda that is constant of motion. K mu is the for momentum. Shape of iron line depends on background metric, inclination angle, inner and outer radius of accretion disk, and emissivity profile. We fix inner radius at ISCO, innermost stable circular orbit, and outer radius is big enough that doesn't have any contribution to this iron line. And emissivity profile is as -3. First, I present the iron line of neutron star, a space-time around a neutron star. The stationary and axially symmetric solution based on Ernst potential formulas can be written as this one, where we have the first 5 multiple moment here. That is the mass, angular momentum, mass quadrupole, S3 mass octupole, and M4 max hexadecapole. In order to use this metric for neutron star case, we need the right set of multiple moment. We define the multiple moment as this one, where alpha, beta, and gamma are equal to 1 for the Kerr case. J is the spin parameter, and M is the mass parameter. The space-time moment of neutron star can be defined as by 3 parameters: mass, spin, and quadrupole moment. The relation between these 3 is as these 2 case. The equations is only depends on mass, spin, and parameters alpha. The parameters alpha, depending on the rotation of the neutron star, can vary from 8 to for the highly rotating case, and 1.5 for non-rotating case. This is the iron line of this metric. The spin parameter is 0.5, inclination angle with the viewing angle is 55, and for different value of the alpha, I plotted the iron line. As we see, there are some effect here, and we will see that if we can constrain these lines or not, we can constrain these parameters or not. This is the iron line for case spin 0.2 and different value of iron line. As we see, there are not a strong effect here, and the effect is weak. And we don't expect to constrain parameters in this case, but we will see if we can do it or not. In order to analyze reflection spectra of a black hole binary to test our K parameters, we simulate data. Our data simulation consists of a power law model with photon index gamma 2 and one of single iron line of our code. The information about our simulation is here. Equivalent with exposure time and flux is written here. And we simulate data with LAD instrument on board of EXTP mission, that is China-Europe X-ray mission, that is planned to be launched before 2022. Its total effective area is very large, and then we feed out data with power law model and a reline model. We have 8 free parameters here: photon index and normalization of power law, spin and inclination angle of black hole, 2 emissivity index of broken power law and breaking radius, and normalization of iron line. Here is a test for our data simulation to see if there is a discrepancy or not. This is a Kerr case. We produce the data of Kerr, we put the metric of Kerr, produce the data of Kerr case, then we fit with a reline that is Kerr again. We see that the reduced chi-square is good, and there is not unresolved feature here. This is data to model ratio. The iron line that I'm talking about here, it is a feature in the spectra. This iron line is here. For the neutron star iron line, we see for the spin 0.5 and alpha 8, the reduced chi-square is 2.1, and there are unresolved features. But for this special case, we don't expect to put constraint on it, because there are some, even though there are unresolved features here and reduced chi-square is not good, but there are systematic effects that may affect this, and we cannot constrain it. But for the case, for the spin 0.2, alpha 2, the reduced chi-square is good, and there are unresolved features, and we don't expect to put constraint for these parameters. We have a good fit with Kerr that cannot be considered. I mentioned again, we produce data of iron line, then we fit with the Kerr. We see that Kerr can fit this data, and there is parameter degeneracy here. The second metric that I'm considering here, it is Cartesian spacetime that contains mass, spin, and not parameter as gravito-magnetic monopole charge. And for the 0 n, we have Kerr case, and for different value of a and n, we can have a Cartesian black hole or Cartesian singularity. This is iron line of Cartesian spacetime. This is for spin 0.5, spin 0.8, and 1.5. And for different value of n, we see there are a strong effect here, and we expect to constrain this. There are a strong effect here, if you see. This is for the case for spin 0.8, inclination 55, and n 1.5. But here the simulation is for current observation as new star data. This is for simulation with new star telescope. The fit is, as we see, the fit is good, and we cannot distinguish between iron line of Kerr spacetime or iron line of Cartesian spacetime. But if we have repeat this calculation with EXTP mission, we see that for spin 0.8, inclination 55, and n 1.5, the reduced chi-square is not good, and there are unresolved features. So we expect to constrain our parameter in this case. Electromagnetic-based tests of strong gravity regime are parametrically degenerate, and also current available model of spin measurement is based on Kerr model. This parameter degeneracy in testing the metric is problem to measure a spin of compact object and constrain possible deviation from Kerr solution. For our neutron star iron line, for higher value of a spin, such as 0.5 and alpha 8, even though the fit is not good, but due to systematic effect, it is harder to constrain it. The fit is not too bad for spin 0.2 and alpha 2. This means that it may be hard to constrain possible deviation from Kerr in this case. For KTN iron line, we find that the KTN of FEI line can be resolved by a Kerr iron line with no star observation. That is parameter degeneracy here, but it cannot be fitted by XTP observation that is may be constrained. To summary, I want to say what we are doing here. We are trying to test Kerr solution with electromagnetic radiation. We employed iron line method, but one can use QPOs, black hole shadow, or iron line reverberation mapping and continuum fitting method to do this test. We simulate iron line of reflection spectra with our ray tracing code, and we also simulate data of a black hole binary, and we analyze our data. In general, the electromagnetic-based tests of a strong gravity regime are parametrically degenerate, and in order to verify Kerr solution, our deformation parameters should vanish. Thank you.
Thank you very much, Dr. Ghasemi. We are ahead of time, so I think we have time for a couple of questions. If anybody has question, raise your hand or
Hello.
type your question.
Can I ask one question?
Yes?
Yes, please.
Thank you for your talk. I'm wondering about the slide number 14 to 18. It seemed that the yes, here. I think it seemed that the wide range of error bars in comparison with the data points results in good values for reduced chi-squares. I think that other methods like
panel is very big. It is not the Lagrange errors.
I think that the error bars in comparison with the values of the points, data points, is very high. And in reduced chi-square method, it results in very good values for chi-squares. I think that the other methods, like other tests, can be a reasonable test for this kind of data.
Okay.
Thank you.
Thank you.
Sorry, can I say something?
Yes, Dr. Roshan. You can ask your
About
question.
the error bars, I think that they do not reach even to 1% error. You know, they are not too large. If you see the y-axis here in this page, then they are not too large.
Yes.
Am I understanding correctly the question? Masoumeh, do you think that the error bars are
No.
low? Okay. Thank you.
Okay, any other questions, comments? Please raise your hand if you have question.